Hey guys, and welcome back, and this week's video is going to be about compound interest, and more specifically I'll be showing you and explaining to you the formula for compound interest that you have in your IB formula booklet, at least for Math AA. And I want you to get more familiar with this formula and understand where it comes from and what it means so that you can therefore use it most optimally and you will actually be understanding what you are doing and not simply plugging values in. So this is the formula that you have in your IB booklet, and it states that your final value of your money is equal to your present value or initial value times, in brackets, 1 plus your rate of interest over 100 times k, all of that in brackets, to the power of k times n, where k is the number of compound periods per year, r is the nominal interest rate per year, and n is the number of years. And this might look a bit complicated, convoluted, and you might not really understand what each number is for, but I'll show you exactly what this means and why it totally makes sense. So first of all, what does the word compound even mean? Because as soon as you understand that, I feel like you understand the entire concept. Compound means to add. So why this is important is because unlike simple interest, we're always adding onto our previous value. So I feel like we've all been familiar with this type of example. At the beginning, you have 100 euros, and then you invested with something that gives you 10% interest. So then by the end, you'll have 110 euros. But the next year, instead of taking 10% from the 100, you're taking the 10% from the new 110. So you get, instead of plus 10, you'll get plus 11 euros, so you'll have 121. And then we continue going, so that next year, instead of having 10% of 100, you're again going to have 10% of, in this case, 121. So you're going to have 133.1, and then you keep going. So you're always adding on to, and you're taking the percent of your previous value. So let's look at what this looks like yearly, because I feel like that's first how you get the hang of it. So let's say that our interest rate is 5% at the end of each year, so yearly, and our value that we're starting off with is $100. So what would our money be worth in 1 year? Well, this part is quite simple. You have, in 1 year, you're going to have 1,000 times 105%. And how do you write 105%? Well, you can express it as 1 plus 5 over 100, because 5% as a decimal is equals to 5 over 100, and then 100% as a decimal is just 1. So you're adding that to get 105%. So you're going to have 1,000 times 1.05. which gets you $1,050 by the end of the first year. Now the second year, and remember again back to what I said about this being added on. Now we're going to take the 5% from this. But what if we don't want to do all of these intermediate steps? What if I want the second year right away? Well, then I can just write my first expression, and then I know that I will have to take again my present value, which in this case is this value right here, and multiply it again by my interest. So then I'm going to have 1,050 times 1 plus 5 over 100, which is going to equal to $1,102.5. Let's repeat this logic with year 3. In year 3, we're going to take our present value, 1,102.5, and multiply it by 105%. If we don't want to find this first, we can simply write this value right here in terms of our initial value, our first year before we got the interest value. So we write 1,000 times 1 plus 5 over 100 times 1 plus 5 over 100, which is 1,002. And then we finally multiply that by 1 plus 5 over 100 again to get, by the end of year 3, what our value will be. And in this case, we're going to have 1,157.6 So if you can get the pattern of what we're doing, we are always going to have our initial value and then we times it by 105% in this case, right? But then if we don't want to keep on finding these intermediate values, such as the ones I'm highlighting right here, we can simply express our, for example, third year in terms of our previous or in terms of our present value during the first year. So we're going to have 1,000 and times 105% 3 times because we're doing it for 3 years. So if we try to generalize this, we're going to end up coming up with a formula that says that in this case, we're going to have 1,000 times 105, because that's what this expression simplifies to the power of n, where n is the number of years. Because in the first year, we had to multiply it once. In the second year, we multiplied it twice by 105%. And in the third year, we multiplied it 3 times by 105%. And if we generalize this even further, we can say that it's our present value times 1 plus our rate over 100 to the power of n. Because this right here gives our percentage in terms of a decimal, which is what we want. And this multiplies it as many times as the number of years that we have compounded our interest for. So this leads us to our first general formula. However, you might realize that this looks a bit different from the one in your formula booklet. And why might the case be? Well, it's actually quite simple, because what if you don't want to invest your money every single year and only get interest on that? What if you want to get interest every single month or every single quarter? What do you do then? Well, in the IB, it's often that you see a question that says, at a nominal annual rate of insert percentage compounded, and it's not necessarily annually, but it can be semi-annually, it can be quarterly, it can be monthly. And what does that mean? Well, it means that instead of having 3% at the end of each year, you're going to have 3% overall yearly, but those will be split into further time periods. So for example, if you had 3% quarterly, then every single month you would get 3/4% on your money. If it was semi-annual, you would get 1.5% on your money. If it was monthly, then you divide 3 by 12 because there's 12 months in a year, and you would have 0.25% each month. Now, how do you express this if we want to build upon this formula that we have built right here? Well, in this case, our percentage is going to be a little bit different. So we're still going to have our present value times 1 plus a certain percentage. However, in this case, it's going to be r over 100k to the power of kn. And why might that be? Well, because you're still using the number of years, right, in your formula. You want n to be your input. So overall, if we see this procedure that I have followed right here, we can see that if we have our rate and we split it by the number of times that you have it per year, because remember, this rate right here is our annual rate. So this is these rates added together by the end of the year. So we divide it by the number of times that we do receive interest on our money, and then we further again divide it by 100 to get that as a percent. So for example, here it would be 0.015. And then we add that to get a percent that we multiply our present value by, for example, 101.5%. And this is where this formula comes from. So this is our number of years, and this is our number of compound periods per year. And the key to this is understanding that when they say an annual rate of, for example, 3% compounded, let's say monthly, they don't mean that you have 3% every single month. They mean that by the end of the year, you have 3% total, but those 3% are split into each month, such that in the end, in this case, you'll always get 0.25% every single month. And then you incorporate that into your formula right here. So just quickly to illustrate, say you have X amount of money, and then by the end of first month, you're going to have X times 1 plus 0.25 divided by 100. By the end of the second month, you'll have 1 plus 0.25 divided by 100 to the power of 2, and so on. And this is where the k here comes from, because in the end, you'll be doing you won't be doing a compound period every single year, but you'll be doing it every single year times the amount of compound periods per year. So for example, if we did monthly, we would have 12 compound periods every single year. So when n equals 1, we're going to have 12 compound periods because we're going to be compounding our money every single month. So finally, let's solidify this example. Let's say that we have a nominal annual interest rate of 3% and we compound it quarterly. And we first invest 3,000 euros. How much will you have after 15 years? Well, again, remember that if we follow the logic, then our final value is going to be 3,000 times 1 plus 3, but in this case, we're compounding quarterly. So divided by 400 instead of 100. And maybe a way that you understand it better is if we write it separately, divided by 100 times 4, because dividing 3 by 4 first gets us our quarterly percentage, and dividing it by 100 just expresses our percentage in the form of a decimal, so we can use it. And then quarterly, so we're going to have 4 times n, right? Because in a year, we're going to have 4 compound periods. Now, all we have to do is set n to be 15. So our final value after 15 years is going to be 3,000 times 1 plus 3 over 400 to the power of 4 times 15. And if you plug that into your calculator, you'll end up getting that you will have approximately 4,697 euros after 15 years. So I hope this makes sense. I hope you understand why, for example, what the k means, where it comes from, and why it's times the number of years. And if in doubt, just do some practice questions and try to get a feel for this formula. But I hope you're more familiar with it, and see you next time.